So for our last example, I want to show how we can use a pendulum to measure local changes in gravity and see how sensitive that is. So this is problem 49 in your book. A pendulum, just like a weight on a spring, is going to oscillate, but it's independent of the mass. Instead, the oscillation period is equal to 2 pi times the square root of the length over gravity. So if I've got a pendulum of a certain length, L, and it's swinging, and it's doing this in a gravitational field G, then if I measure the period, I can measure the acceleration due to gravity. And if we went out into the, or if we were in the laboratory and we knew that gravity was equal to 9.8 meters per second squared, calibrated, we've measured that, and we measured this pendulum to have a period of 2 seconds. Pretty precisely, like to several significant figures. Now let's say we took the same pendulum out into the field someplace and we measured the period to be 1.99796, so a very small change in the period. How sensitive is that to change in gravity? So I'm going to say the original period was t naught. My new period, we'll just call that t. That means I've got another ratio problem. I get 2 pi times the square root of L over G divided by, and we'll call that G naught because that's in our laboratory measurement. And the length has not changed, so I can cancel out all of that stuff, and I wind up with just the square root of G over G naught, like that. And so I can get my new value of G. It's just going to be my old value of G times the ratio of T naught to T squared. And since T naught, we'll call that T naught. T naught is larger than T. I'm going to get a number that's larger than 1. So I get 2.00000 divided by 1.99796 squared. And if I do that, I wind up with a G that's slightly more, 9.82 meters per second squared, which is small, but measurable, right? Measurable with this pendulum. And this is one way that you can design a device that could detect changes in the acceleration due to gravity.